Welcome to the Falconer Lecture Series. My name is Jeff Friedman. I'm a research faculty at the Atmospheric Sciences Research Center here at the University of Albany, State University of New York. It is my pleasure to present Dan Kirk-Davidoff, who is the principal technical leader, as you can see, at EPRI, the Electric Power Research Institute. He's part of the Energy Systems and Climate Analysis Group, and I've known Dan for many years now, it seems, right? About at least, yeah, quite a few years. Yeah.
I knew you before I got here, so
Right.
at least 10 or 12.
Yeah. So, and Dan and I have worked together before in other projects involving climate change, as it turns out. He's research focuses on the impact of anthropogenic climate change on the electric power system. And particular sensitivities of the electric load and renewable generation technologies to climate and weather extremes. And an improved simulation of load and renewable generation and planning for future electrical grids. This is a huge issue these days in terms of the utility and power grid industries. He also develops information resources on climate data for power system planners. Now, before Dan was at EPRI, he worked as a faculty member at the University of Maryland, where he developed observational strategies for satellite climate monitoring missions and did climate modeling research on paleoclimate phenomena, including Messinian desiccation and Eocene polar warmth. Wow. And in private industry, where I first met Dan, where he developed forecasting systems for wind and solar generation, combining numerical weather prediction, satellite image processing, and machine learning. And he led the development of a modernization plan for the Uganda National Meteorological Authority. Dan earned his Bachelor of Science degree in Geology and Geophysics at Yale College and a doctorate in meteorology from the Massachusetts Institute of Technology. And so without further ado, as one says, I present Dan Kirk-Davidoff.
Yeah, thanks very much. Appreciate the opportunity to talk with you all. So I work now at this Electric Power Research Institute. We're a nonprofit research organization we're a membership organization, and our members are utilities and grid operators, initially just in the US, but now really all around the world, and that will come up later on. So we're a nonprofit in the public interest. So although the questions that we are oriented around have to do with the curiosity and interests of our members, we have a really high value on dispassionate and honest analysis. And we want the results of our research to be as broadly available as possible, consistent with the members still wanting to pay their dues, feeling like they're getting a good deal. But a bunch of the stuff that I'll talk about tonight is all publicly available, and I'm really happy about that. It was the first thing that I worked on when I got to EPRI 3 years ago. Was that no, it's coming on 4 years ago. Was this program called Climate Ready for Climate Resilience and Adaptation Initiative. And that all of the material that was developed under that program is available to the public for free. I'll show a little QR thing that you can scan later on, or you can just look up EPRI Climate READI Climate Ready and find all that stuff. And so since I've been at EPRI, as Jeff was saying, I've pursued these sort of two aspects of the problem. On the one hand, the climate change impact on the energy system, which we wanted to understand pretty broadly to include lots of forms of change, because the sort of the trends involved in that result from greenhouse gas warming are, of course, really important to understand, and their impact on the energy system is important to understand and mitigate. But there's also just our infrastructure that we have in the world today is not optimally designed for the climate that we have today, because until really recently, we didn't really know what the climate of today was all that well. If you're thinking about when, most of the engineering practices that were involved in our current, infrastructure, building power plants, building power lines, building roads and dams and all those big civil engineering projects. A lot of the practices and procedures for that stuff were put together, what, in the 1950s, 1930s, 1920s, when at best you might have like a few years of observations in a lot of places, and you wouldn't typically be able to make much of an educated guess about what the 100-year event was, right? What is the event for which that's so intense that there is only a 1% chance of it occurring in a given year? Obviously, you can choose different thresholds depending on how long you want to be planning for and what level of risk you're willing to entertain. But it's reasonable to think that if you're going to build something and sink a lot of money into a piece of infrastructure that you expect to last substantially as you build it for, 30 or 40 or 50 years, you would like it that you shouldn't have a 50% chance of, some weather event blowing it all away, right? So we'd like to build things in such a way that they can withstand something like a 100-year storm if we expect them to be around for 30 or 40, 50 years with some confidence, right? So that's the kind of question that this talk is oriented around. And let's see, here we go. How do I advance? What am I missing?
The laptop.
I tried down arrow. Should I do return? Oh, or just
You have to
tap.
be here.
Oh, okay. Whoop, no, I've gone too far. What did I do? Oh my goodness.
What did you do? What happened?
That is it.
Wow. Now something got switched off behind. Oh, this
Oh,
how I
did I
got.
touch the, oh,
Okay,
Yeah, yeah.
so we
yeah.
can't go that far back. So you're gonna have to reboot that. That's fine.
oh man, I'm so sorry.
No, there's nobody's fault here. This is just one of those things that happens. There we go.
Yeah, well.
What are we-
Don't touch that.
Okay.
That's
That's
not
it.
needed. It should.
You need to both displays. Displays.
It will come up
It will
after
come up.
it goes
When the screen
comes
comes down.
down, and
Okay.
then it will, because it got switched off the.
Okay, I'll vamp. It's okay. Anyway, the work that I'm doing today came up because back in April of 2024, there was a big storm in a country that is somewhat in the news today because it is south of the Persian Gulf, or what those folks call the Arabian Gulf, depending on which side you're on. And it destroyed a very large number of solar panels. And so the people who get the electricity from that panel wanted to know, what did we miss? Was the system not built ruggedly enough, or were we for what we should have for winds that we should have expected, or did we not know to build to a high enough standard because we didn't have a good enough sense of how strong the winds ought to be? Are we gonna?
It takes a bit of time because once it shuts down, I think it has to cool down and then.
Oh,
start
goodness.
again.
Okay.
Okay, so
It
display
says-
is on. Yeah.
It
Okay.
says on.
I'll keep vamping. It's okay. Yeah.
Oh.
Oh no. Okay. Oh, now it's on here. That's good.
And
Starting to whir.
Okay, great. I'll stand back here so my.
just turn the screen around there. No, yeah, we do.
Yeah. Zoom folks, we accidentally touched something that turned the screen off.
Okay,
and,
it's coming.
It's coming. It's warming up and getting back in gear. I apologize for the delay. Yeah. Yeah.
The question, so.
Anyhow, the really interesting aspect of working with big solar farms is that they're very heavily instrumented. So I'll get back to that in a moment. Anyway, motivations, right? I was looking around for pictures of like destroyed solar panels, but then I thought, oh, these are all probably copyright protected, and I don't actually have my own picture of destroyed solar panels. But I do have a picture of my own house, right? So this is the kind of event we're talking about. There's a big branch of the very large Norway maple that the neighbors own and is next door. And we had a big windstorm a few years back, and it dropped a big branch there and another big branch on the main roof, and we had a very large insured loss, fortunately, that was taken care of with a new roof. Fortunately, no wood was destroyed. It wasn't too bad, but it's the kind of event we're talking about, right? So we've lived in this thing. There are now, actually. Fortunately, there weren't at the time. So but then I would have had a nice picture of destroyed solar panels, if only. So honestly, the other night, I don't know if you're all up around midnight on when was that? Like, when was that big frontal passage? It was about a week ago Tuesday, I think. And I was woken at around midnight by, howling winds, and I spent the next half hour wondering, are that my solar panels going to be destroyed by a wind gust? But this one only destroyed roof, didn't destroy solar panel. But the question is, how often should we expect an event like that to happen? So on the tree that's in our backyard, we now have a pretty good measure that this is like the one in at least, well, this is something close to the 1 in 10 year event because it's happened once in 10 years. Obviously, one would want to wait 30 years and have three such events in order to be really confident in an estimate that this is a 1 in 10 year event. It might be a 1 in 50 year event and we just got unlucky, or it might be a 1 in 5 year event and we've just been lucky so far. So that's really the question we're trying to get at, is how often am I going to get a wind that's strong enough to cause damage? In this case, blowing limbs off the tree that might destroy something on my rooftop, because I live in a city that's pretty built up and I don't really anticipate having, winds that are on their own strong enough to like rip the solar panel off the top of my roof, although one never knows and one ought to be prepared or understand what the odds of that are. So in order to do this project, when I heard about this project, I thought, okay, this is going to be no problem because, they may not know it, but most of the world, many people in the world know that there's this really awesome thing called the ECMWF's ERA 5 reanalysis, which I think ERA 5, I think it stands for ECMWF reanalysis. And it is really useful for a lot of stuff. So what a reanalysis is the result of a procedure where you take hopefully a very good weather forecast model that has, and a weather forecast model has to start from right now and forecast into the future. But if it's going to make a good forecast of the future, then of course its understanding of what is going on right now has to be very, very good. And that when I was at the University of Maryland, one of my colleagues there was Eugenia Kalnay, who has one of the highest citation counts in the world because she worked on the first American reanalysis, that the NSEP NCAR reanalysis, and her name is, I think, the first name on that paper, and there's about 1 million citations of it. I'm slightly exaggerating, but it's a large number. So it's one of I bring her up because her work and the work of people who do similar work to hers is probably one of the main reasons that weather forecasts have improved dramatically over the last several decades. So on the one hand, the models are just generally better, but on the other hand, we have a much better understanding of how we initialize the models so that they're not starting, from junk, right? Because garbage in, garbage out. If you start with an error in your initial conditions, it will very swiftly grow because of the chaotic nature of the atmosphere. And if you start with the right kind of error in the initial conditions, that is to say, a very physically unbalanced condition in the atmosphere, then the error might just totally swamp the real dynamics of the forecast, and you just get junk out of it. And that's what happened. The very first guy to try and do a numerical weather prediction forecast back in 1900, early 1900s, he had it in mind that we would just pay lots of people to sit in a stadium and do calculations at every grid point and then pass those calculations on to the person on their left and the person on their right. That he worked through a worked example of a numerical weather prediction forecast, and it failed dramatically. And what people only realized later on was that he had some of the information in his initial conditions resulted in a big gravity wave that sort of swamped everything else interesting in the model. And so we didn't have a good forecast. So what we've learned to do over the last 30, 40 years is initialize models in such a way that the initialization process is aware both of the errors in in every measurement, the potential errors in every measurement, and of the laws of physics of motion of the atmosphere. So the goal is to put together an image of the whole atmosphere and maybe ocean system that is consistent with all the observations that we have within their margin of error, but also consistent with the laws of physics and is balanced in such a way that we don't have like, big big unbalanced wave motions that are going to swamp the forecast. Okay. So once you have that tool, this tool of reanalysis, it enables you to do this tool of data assimilation that allows you to estimate the present state of the atmosphere with very high accuracy. It allows you to do this wonderful thing, which is that you can go back in history and redo the analysis for, every hour, or more, I think more realistically, you do it for every 12 hours and then run a short forecast out for 12 hours. And then you have an image of the state of the atmosphere that starts maybe 70 years ago when we first had a reasonable number of observations of the atmosphere in the world, and goes forward up to the very present. So we have hourly information about the three-dimensional state of the atmosphere. Almost any variable you would want is in there, and it's pretty accurate. It's not perfect. For one thing, the further back you go, the less data that you had to initialize the system. Presently, we use a lot of satellite data, for example, to initialize the forecast, but that didn't exist in a regular usable way before about 1980. So the data that you're using to initialize the forecast is really different over time. On the other hand, it turns out that once you know a few things about the state of the atmosphere, there aren't probably that many states that are consistent with that. So even if you just have a pressure map of the US and Europe, you get recognizable results out of that. And so there's this thing called the 20th century reanalysis that started in 1900, way back when at the beginning of the time for which you had a decent number of like temperature and pressure observations. And that gives you, a remarkably believable view of the atmosphere, even back at a time where we had very few observations, certainly of the interior of the atmosphere. Enough about that. But the point is, I can go to what I thought I would do going into this was, well, I'll pull the winds out of the ERA 5. I will correlate them and do a little bias correction against their observed winds at their location where the damage was done. And then instead of just having however many years of data they had from the location of the solar park, now I've converted that, I've sort of bootstrapped that into a 70-year record of data, and I'll have a much better understanding of what like the 100-year storm would be than I would looking just at the few years of data alone. And as I started into the process, I realized that they had already hired a couple of engineering companies to do studies of what the 100-year storm would be in that place. And they had done the sort of defensible engineering approach of just taking the 5 or 7 years of data that they had, fitting it to a standard distribution, and then extrapolating to 100 years. So, well, we've had this many years of data, so we'll just extrapolate that out essentially to the 100-year event. And in doing that, they also had to make all sorts of assumptions about the relationship between wind gust and observed wind, that I was pretty quickly able, by looking carefully at the data that they had, to recognize that they weren't true. So I was feeling a few months ago as I got into the project, like, this is going to be awesome. We're going to make a much better estimate than what they have available to them of what the return period of these storms are, and it's all going to be beautiful. However, as I started to analyze the relationship between the ERA 5 winds and the real winds, I came up with plots like this. Now, this plot, I'm not showing any data from this unnamed client member that I'm working with, but this is just from a automated airport station in Texas. Wait, SPS. Yeah, this is Wichita Falls, north and west of Dallas in Texas. And it has data. There's this beautiful website, which if you all are like, probably a lot of you are weather enthusiasts, I think. And so you probably all know about the Iowa State Mesonet site. And those of you who don't should totally look it up, because it's just wonderful. Like, you think you have a question about what was the weather like at some location in the country on this day, and you can find like, 1 minute wind data for every automated weather station in the country there. It's like an incredible service that I don't know how they fund, but they should be praised and thanks, because it's really, really beautiful. Anyway, so this is observed wind gust maximum. So I've just taken, I think it's a 1 minute time series that's available on the website, and I've taken the hourly maximum of that. And I'm comparing it to a product that's in the ERA 5 data set, which is their wind gust product. So they also have like this, the 10-meter surface wind, which is like an hourly mean. And trust me that that would look much less beautiful comparison. But this one, I mean, if you just look at that blob of points, it's like, well, it's a pretty decent correlation. I mean, R squared 0.54, so, you know, correlation of, whatever that is, like 0.7-ish. I mean, that's not bad. It's a nice relationship. On the days when it's windy, it really is. When the model thinks it's windy, it really is windy. When the model thinks it's not at all windy, it really isn't very windy. But oops, what are those points way up on the top there? That's really bad because those are the windiest days that ever happened in this data set. And ERA 5 had no freaking clue that it was that bad. So what's going on? So when I saw that, I thought, oh, well, this is a problem, but this is awesome. This is a great opportunity. I'm going to really, really make this all better because it's going to be AI to the rescue. Because if you've got, points like that, okay, well, ERA 5, it's a really good reanalysis. So sure, it didn't know, maybe there was some big thunderstorm that came through on that day. It was a very vigorous storm, but it was small. And ERA 5 reanalysis is done on a grid of a quarter of a degree. So like 25 kilometers by a little less than 25 kilometers. So a big thunderstorm can be very powerful and impactful and barely fill a single grid of that model. So the model can't reproduce a storm like that. It doesn't have the resolution to capture it. So, that's excusable, but surely the model, which has such a good, by and large, is really understanding the weather pretty well. Surely it has information in it that would lead you to think that there'd be an elevated chance of a high wind event like this. So presumably, what could lead to, a really strong wind event like that? Well, if it's due to to a pretty small thunderstorm, there's two possibilities. One is that the winds aloft were really strong, and the thunderstorm was mixing things vertically and bringing the momentum a couple of kilometers up in the air down to the surface. And then another possibility is it's just a downburst, which I remember learning about I don't know, in college, or, it was because at that time, this was a huge forecasting challenge. There wasn't good enough observations around airports. And so you could have these downbursts how many people in here have the image in their head of the airplane taking off and the downburst and the resulting crash of the airplane, right? Because you get, the downburst, there's a bubble of air aloft that has rain in it. It falls through some dry air. The rain evaporates. It's now much colder than its surroundings, therefore denser. And so it plunges dramatically down to the surface and hits the ground at maybe 70 miles an hour and then goes splat and boom, goes out to the sides again at 70 miles an hour. And so the idea is if you're an airplane going through that thing, you first encounter winds that are headwinds. And so you're great, you go up, but then maybe your aspect gets a little funny. And then all of a sudden you're in following wind. So your airspeed has collapsed and you stall and you hit the runway. And this was a problem at American runways at the time. And so there was a lot of work put into understanding downbursts. Anyway, I go into that because that's the other possibility. Even if there aren't any strong winds aloft, a thunderstorm can generate really strong winds at the surface if there's relatively cold, dry air in the environment, but it's hot and humid at the surface. You get these saturated parcels of air that rise up through that. Then they make rain. The rain falls through the dry, the thunderstorm is a little tilted, so the rain falls through the dry environment, cools rapidly, gets dense, falls to the ground, goes splat. So I figure, well, ERA 5 may not know that there's the thunderstorm there, but it ought to know that there's the potential for this kind of a storm. So there are some measures of that. You could look at the CAPE, the convective available potential energy. That's just the measure of could you have a strong thunderstorm that day. Or you could look at the DCAPE, the downward convective available potential energy, which specifically measures the potential for this kind of a downdraft. So I figure this is going to be no problem. It's all going to be beautiful. Okay. Intermission. The way I said, I had planned this because of my big vamp earlier. This is a little bit different than my slides are not quite in the order that makes sense right now. But we're going to have a little intermission, let that all sit, and I'm just going to talk briefly about Climate Ready because this is a wonderful thing that we've all worked really hard on, and it's publicly available. So there's the QR, but you can just look up Climate Ready. I really hope why does it keep advancing automatically? It's annoying. But anyway, and climate ready, as I said, is about resilience and adaptation. And we want to understand the risk that aspects of the energy system are under as a result of climate change, but maybe just as a result of being in an atmosphere that we don't fully understand. So we like to think about the risk in terms of a risk propeller. So the risk to things that we care about consists of the hazard, the exposure, the vulnerability, and the response. So the hazard is like the strong wind event. The exposure is there something in the way of that event? So that might mean a tree, that might be, compound hazard exposure connection where, you've got a tree that's vulnerable to the wind, and then you've got a solar panel or a roof that's vulnerable to the tree, right? And then you've got vulnerability. How we need to measure the properties of the system or be aware of the properties of the system that make it vulnerable to the hazard of concern, which might be strong wind, or it might be hail, or it might be lightning, or it might be floods. All those things could go in it. And then, of course, the risk, that is to say, the odds of something bad happening, of damage happening, is also a function of what we do about the vulnerability. So we want to include the response as it currently exists and as it might exist in the future, so that we can, if we want to calculate, is it worthwhile to do some intervention, we have to be aware of all four of these things. We have to know, is the risk changing? Is the vulnerability changing? What is the risk? What is the vulnerability? Is the hazard changing? Is the exposure changing? Is the vulnerability changing? And are we changing our behavior around these hazards and exposures? All right. And likewise, you can think about each of these aspects in terms of sort of components of our mental map. So exposure, when we think about exposure, we should think about some set of bits of infrastructure up there, like a wind turbine or a solar panel or a cooling tower. When we think about vulnerability, we might want to have kind of an analytic mental model of what that looks like. So that might be curves of increasing vulnerability. So as the hazard increases on the x-axis, the odds of something bad happening would be increasing on the right axis. And we have all these vulnerability curves in big spreadsheets with references in Climate Ready for people who really want to get into that level of nitty-gritty. In hazard, we might have a mental map of all the different kinds of bad things that can happen to pieces of infrastructure around the country. Okay. Oops. Just trying to keep in the camera for those who want to see my face. And we can also think about the kinds of hazards that climate and climate variability might pose to infrastructure in terms of different time frames. So there's acute hazards like the ones we're talking about today. Is it going to be a severe wind event? Is it going to be hail? Is there going to be lightning? Or we might think about a heat wave that results in very high demand on an electrical system that might lead to outages. But we can also think about chronic hazards that might involve energy constraints. So if we were, as we build a system that's more and more dependent on renewable resources, we have to worry about, well, what happens if not only, the sun, obviously there are going to be days that are cloudy, but what happens if there's 10 cloudy days in a row at a time when we were counting on that energy? How do we build up our systems of storage, whatever they are, to make sure that they're sized appropriately for the variability of the climate as it's changing over time? Okay, back to our main story. This is an example of the kind of process that I went through to try to figure out what I could use within the ERA5 reanalysis to understand the odds of a bad thing happening. So here, for example, in blue, let's see, where's the bad thing? The red is the observed daily maximum wind speed. And there you can see, like, this is actually the event I mentioned. This is the event on April 16th, 2024. You see that huge red spike there. That's in meters per second there in this case. So that's a 35 meter per second wind. That's, 70-ish knots. It's a very strong wind event. And that's not the strongest observation. They had observations that were more like up in the upper 40s. So there were very, very strong winds that day. Well, what else was going on? The Arrow 5 didn't capture it. Arrow 5 gust never gets above about 14 meters per second on that particular day. So what else can we look at? Well, in this case, I was like, ooh, this is nice. There was a somewhat elevated 500 hectopascal, winds 5 kilometers up in the air were a little bit elevated. And then if you look at the blue curve down there, it was also a day when there was a lot more CAPE than usual. So that seems promising. Like if those things are aligning for this event, then it ought to be the case that I could come up with a probabilistic model using what I used a machine learning code called XGBoost that is pretty good at combining lots and lots of different predictors and looking at the interactions of those predictors to get at a predict-and. And it can not only just do a sort of regression fit where I just want to turn, okay, here's a whole bunch of numbers that vary over time, and I want to turn them into one number over time that best approximates the thing that I care about. It will also do a classification forecast, which means it's going to predict the probability that something that I care about is in one class or another. In this case, I would say, is the wind above 70 meters per second or below 70 meters per second? What are the odds of that? So that was the plan, was to put as much as I could all in big matrix and see what I could find. And the depressing result was that I got only a very modest improvement relative to the wind gust. So I thought, okay, well, the problem is that I only have a few years of data. I only have I have high resolution data, and that's nice, but there just aren't that many really extreme events in this data set. Why don't I try something better? And I looked around in the literature whether anyone else had done that. And sure enough, Marina Estitha had done almost exactly the same idea. Actually, I had already done some of the work at that point. And I talked to her. And the interesting thing was that she was really focused on the Northeast. So when we got to talking, I realized that she hadn't done what I had planned to do, which was including the DCAPE as a new predictor, because it's not sitting there in the Era 5. It's not one of their, easily, it's not a pre-calculated number there. So I was hopeful, having done a little bit of work and having talked to Marina, that maybe I had done something that she hadn't done, because her main result was, yeah, the Era 5 gust analysis is okay, but not great, and you can improve it mostly by including the 850 hectopascal winds, which, although on this particular date they were somewhat elevated, you can see they're nowhere near the highest in this record. Like there are other days where it was a lot higher. So it turned out that was a very bad predictor in the Middle East. It really didn't improve the forecast at all. And I thought, okay, well, that's probably because like you got an event, you're getting like 40 plus meter per second winds at the surface on days when the winds aloft are only, actually at the time of the event, they were already down from their peak. So they're maybe like 25 meters per second. So even that particular event, it probably wasn't a major cause. And by and large, when I looked at a larger number of events, it didn't really seem to be much of a predictor at all. But I thought, okay, where can I go to get longer time series and lots more data? And so I turned to the Iowa State beautiful website and realized, oh my gosh, look at this. I can pull all this data from stations across the South Central US where there are convective events with strong winds that happen all the time. So this was just back in January, I pulled like 7 stations from the year 2000 to 2025. So now, and it turns out that these kinds of events are not that well correlated spatially. So there are some events that show up as strong windy days all across those stations, but there are a lot where it's just at one station and not at the other ones. So I'm thinking this is like having 7 independent 25-year data records. So it's like 125 years of data. I ought to be able to do a little bit better. And to give away the punchline, yeah, I did a little better, like a little better. Here's one event at the event that I mentioned at Wichita Falls. So you can see it's a huge outlier of an event, right? The winds these are in knots now, just because that's what it comes from Iowa State. The winds are 70 knots. This is maximum daily wind for all 365 days of 2016. Boy, that event stands out like a sore thumb. And boy, does Era 5 not want to produce a lot of events like that. So let's zoom in on June, and you can see there it is. There's the event. And now I've got the full resolution. So lots of, actually, this isn't even full resolution. This is just hourly resolution. But you can see lots of little wiggles. And again, a very spiky single hour event over there. And then this is what was going on. Sure enough, just as that spike happens, the edge of a thunderstorm is, this is radar. Another nice free resource. The National Weather Service has a pretty easily accessible radar GIS site where you can pull up radar maps from any day in the past. I think back to maybe about 2008 or so. So nice resource if you want to do this, just do a sanity check, because I first looked at that and thought, oh, it's such an outlier, it's probably junk. But no, sure enough, it corresponds to a real event. It probably was a real outflow from a thunderstorm. Cool. So I looked at 5 or 10 or a bunch of the other events that were like that really stood out like sore thumbs and verified that they were real. I did some data cleaning because there also were some bad points in the data that were just, 100 plus knot winds that weren't real. And came up with what I thought was a pretty good target data set that I'm going to try to predict. And then I pulled lots and lots of variables from Arrow 5. So basically, like everything I could think of, I put everything in the kitchen sink. So Arrow 5 winds gust product, Arrow 5 surface winds aloft at 850, 700, 500 hectopascals, temperatures at surface 800 blah, 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 up to the top, relative humidity, dew point at the surface, relative humidity all through the column, Arrow 5's CAPE product. I calculated a DCAPE product from all of those variables. And then I also pulled the geostationary temperature, geostationary satellite infrared brightness temperature, because I thought, well, I don't have radar, and maybe this would be a decent proxy for these small convective thunderstorms that the model misses. And while I don't have 70, I felt a little bad about it because ideally the goal is to just turn the pure Arrow 5 data into a pure wind gust product. In the world, we have I can get the satellite data back to about 1980, but I can't get it back to 1940. So it's always going to be a shorter data record. But I thought it's a start, right? And 1980 to the present is 45 years. That wouldn't be a bad thing if it turned out to be a good predictor. So I took that and I calculated the brightness temperature. So that's the effective temperature of the highest radiating level in the atmosphere, the thing that the satellite sees when it looks down. If it's colder, that means it's a higher cloud top, probably means more likelihood of bad weather. So I pulled that, but I also pulled points from half a degree away on each side, because I figured if I get them all into this fancy algorithm, it would be able to tell the difference between an isolated cold point, which would be extra impactful, and just some kind of broad uniform cloud deck that wouldn't necessarily be associated with bad weather. So I pulled all those things, and then I went through a process with XGBoost to try and understand which of these predictors was the most impactful and which ones I should leave out, so I'm not doing overfitting, and came up with this list on the right. So we've got, and the min and max mean, so what I'm going to try and do, I went through a lot of thinking around this. And if anyone's done something like this and thinks has some advice, I'm certainly open to ideas. But I figure what I should do is the thing that I'm going to try and predict is going to be the likelihood or the likely highest wind or something like that for a, let's say, 1-day period or a 5-day period or a 10-day period. And I'm going to throw in a bunch of predictors from Arrow 5 that I hope will be, lined up with that 5-day or 10-day period. And so I would take over that time frame, I would take like the minimum and the maximum and the mean of each of the products, with the thought that for some of these variables, it'll be the maximum that's most important, like if it's CAPE or DCAPE, and some of it'll be the minimum, like if it's cloud top temperature. And for some of them, it might be the rate of change over that 5-day period might be the best predictor. But I can't use if it's 10 days, I can't use all 240 data points. That just gets too crazy, too much risk of overfitting. So what I came up with is this list on the right. So the DCAPE minimum, that's minimum just because DCAPE is defined negative. It's the biggest DCAPE. 700 dew point, highest dew point. That's interesting. Not what I would have expected, but that's what came out of the process. and a bunch of things having to do with infrared window channel, both the channel itself and then like the maximum gradient, that's that DD product, is just the biggest change either this way or this way across the point. And what did I get out of that? So on the left is just the skill at one of these stations. This is CDS, which is just a different one of the stations. Of the raw Era 5 wind product, you can see R squared equals 0.57. And on the right, this is the regression model that I pulled out of XGBoost with all of those parameters added to it. And now we're at 0.65. So it's a little better. What I particular note is that now there are some of the high points in the observed record are a little bit further off on the right. So the new product has a bit more of a clue that those are days when it might be windier. Now, the real test of this is going to be in more of a probabilistic mode, because again, what I really want to do is I want to come up with a curve like this, which is the return level, return period curve, right? So this is the return level plot for the observed winds with confidence levels, right? So each of these is an event that kind of falls on this spectrum, and the year in which it happened. I wanted to code the year in which it happened in case there were obvious trends that would shout out at you, but don't really see those too much. And this is the extreme value analysis curve that comes out of that, and says that, the 2-year return period expected maximum wind is like 44 knots, and the 20-year, which is as much data as I have here. So this process only produces data for as long as the time series that I have. You can certainly extrapolate that out as far as you want, but I'm not doing that yet because I'm trying to stay within the range of the data that I have. And it's saying that the 20-year expected return level is about 55 knots at this particular location. And then I really, really was expecting, this is like hot off the press, and it's not good enough. So the model still isn't tuned adequately, because you can see that's the observed gusts on the right, and then a bunch of different attempts to reproduce that with XGBoost. And it's fine that the regression slope is not good enough. The real thing is that I have this stochastic classification scheme where I'm trying to understand, I'm trying to allow it to generate some random events that are as strong as it thinks they could possibly be. And I want that curve to look more like the blue one. And sometimes I can get it to be, but I can't confidently every time. I don't have a procedure yet, and I really need to get there, that confidently reproduces the observed curve. And that's pretty much what I got. So that was like today's result, and that's my last slide. So yeah, thanks very much for your attention. If anyone has brilliant ideas, I will happily, I don't know, take you out to dinner, and I'm happy to take any questions.